Today, I wanted to talk to you about building learning to rank, or LTR models, for search using large language models, also called LLMs or foundation models. So let me introduce myself very briefly. My name is Sujit Pal, and I work at Elsevier Health. I used to be a search engineer, but since then, I moved to doing more and more machine learning and data science work. So nowadays, most of the work that I do is at the intersection of search and machine learning. And as you can see, I have a pretty broad, but probably unsurprising range of interests, given the work that I do. I have been working on a generative AI project since the middle of this year. And this actually started out as a way to do automatic evaluation of our search stack before labels were available from our domain experts. But then it morphed into what I'm going to describe. So it was a bit of a side project. Which we ended up not using finally, but because of its history, I ended up using a lot of the infrastructure set up for this project, the main project, the generative AI project I was talking about. So in any case, here is my email and other social media coordinates in case anybody wants to get in touch, right? One other thing, I have posted the link to the slides and the software in the Discord channel, so you'll be able to get it from there as well. You don't have to copy from here. So in any case, here is my agenda, what I intended to cover. First, I will describe the project at a very high level, and then I will go into the details of the implementation component-wise. And here I will cover some theory in learning to rank models, since I think this may be new to at least some of you, right? And finally, I will cover issues that still need to be addressed and what we are doing or planning to do to address them. With that, let's start. So a few years ago, I learned about this what, why, how framework to read academic papers quickly. And I became a fan, right? So since then, I find that I can apply this idea to other areas as well, such as communicating an idea or describing a project such as this one. So to address the what, that is, what is the big idea here? Essentially, it boils down to getting LLMs to generate relevance judgments for a query with respect to a document. Then using these judgments to train an LTR model, and using the LTR model as a reranker for search, search results. So essentially, the final product is now a search pipeline that has learned to return relevant results based on what the LLM considers relevance. So it makes sense because fine-tuning search is usually a very labor-intensive affair. And so if you can get machines to take you part of the way there, I think of it as a win. So why do I think this idea has legs? Traditionally, LTR has been popular in domains such as e-commerce, where there is a good signal in user feedback, such as views, clicks, add to cart, etc. Not so much in areas like health, where we get our in-house domain experts to hand label judgment lists. It's really backbreaking work, and it's no wonder that it's so hard to get enough judgments to train models. So essentially, what ends up happening is that search engineers would end up treating these labels that get generated as a validation set to validate their hand-tuned changes. Of course, I mean, having this is still better than tuning and hoping that it all works in production, obviously. But if you can harness machine learning to build LTR models, not only do we get this, like a less peaky solution, but in general, it's kind of, gives you a more well-rounded solution. So it's a better solution, in my opinion. And LLMs, especially the large ones, are quite good at mimicking human preferences. So it makes sense to use them for generating judgments instead of human experts. And here, I'll point to this as maybe this is just an appeal to authority on my side. But even teams such as this one from Microsoft Research, they seem to be actively looking in this possibility. And they have implemented this idea that I'm talking about, even though they don't share too many details in this paper. I also wanted to show you the results of my experiments up front as another reason why this idea might have legs. Before we built our LTR models, we evaluated a bunch of baseline search pipelines, pure lexical search, pure vector search, using out-of-the-box Elasticsearch and Quadrant vector stores. Another one was our knowledge graph enhanced lexical search pipeline, hand-tuned by our search engineers over the last few years. And we then trained 4 models, a pointwise regression model, 4 LTR models, basically, a pointwise regression model, and pairwise models, RankNet, LambdaRank, and LambdaMart. And of these, RankNet did the best. And not surprisingly, the hand-tuned pipeline was the winner, of course. I mean, if you look at the top red line here, the ultimate winner, in fact, even although not by a whole lot, as you can see here. So our RankNet model has a map at a mean average precision at 10 of 8.38, whereas the hand-tuned model had 8.50, which I still think is a win, since we approached the performance of the hand-tuned pipeline, tuned by multiple peoples over a number of years with ML models that were built with training data also generated from ML models. So essentially, almost no human effort except for programmer effort. So okay, now on to the how. Here is the high-level architecture. It's a supervised learning pipeline. So there is a training and an inference pipeline. There is also an evaluation bit down in the corner here to validate that the model we trained will perform adequately during inference. And I will cover each of these components in more detail. But at a high level, during training, we want to take some queries, send them through Elasticsearch, generate judgments from the query document pairs that were generated from the from Elasticsearch using an LLM, and then train an LTR model using these judgments. And for inference, we take an incoming query, generate the top 50 search results using untuned lexical search from Elasticsearch, use the LTR model as a reranker to score and return the top 10 relevant results. And for evaluation, we get the LLM to deliver judgments on the re-ranked results that we just saw and use that to determine the performance of the LTR model. So I will refer back to this diagram many times during this presentation, so the steps will become clearer as I continue. So now that we know what the presentation is all about, let's go deeper. First up, query sampling. So in my case, I was trying to build an additional component to an existing search pipeline that would handle a subset of the queries that are already being consumed at the moment, but not handled optimally, right? So I decided to sample from our existing query log. The objective here was to find queries in the logs that were similar to our goal set queries for some measure of similarity, such as similar number of tokens or similar number of medical entities in the tokens. And essentially, I pretended that these two things, in my goal set were normally distributed, and I used the mean plus or minus standard deviation bounds to filter out queries from the log. So the algorithm that I used is basically in the last two bullet points here. And I did a few other things, such as removing non-English and navigational queries from the list. However, depending on your situation, you may actually need to do something different. So for example, if this is a greenfield project, you may need to build up a representative set of queries, maybe doing automated question answering on your corpus, right? Or some other method. Yeah. So next up is the label generator component, which is basically an LLM, a large language model, that generates judgments given a query document pair. So we used Anthropic's Claude for this task. And for the pointwise regression model, you remember, if you remember, I talked about 4 different LTR models. So for the first one, the pointwise regression model, here is the prompt that we used. So we provided the LLM, the query and the document. These are placeholders. They will actually, during the actual work, the query and the document will be replaced by the appropriate query and the document, right? So we provide the LLM the query and document text and prompt it to generate a judgment of relevant or irrelevant. I also ask it to provide the reasoning for the judgment, even though I actually don't use it, in the hope that going through the reasoning will enable it to provide better judgments, similar to zero-shot chain of thought prompting. And the distribution of judgments across the training of about 500 queries here is shown in the bar chart. You can see here. And as you can see, it's not perfectly balanced, but it is good enough to train a binary classifier regression model. For the pairwise RankNet model, our second model, we need to provide the LLM with a query and a pair of document texts, right? So you can see these 3 here. And prompt it to generate a binary document 1 or document 2 judgment, depending on which text is more relevant to the query. So note that you don't need to generate judgments for all pairs of documents for a given query. Just a small subset is enough, maybe 5 to 10%. My strategy was to generate the top 20 documents from Elasticsearch for each query, and then create pairs using the first document as the left-hand side and the other 19 documents as the right-hand side of the pair. So essentially 19 pairs for each query, 500 queries in all. And as you can see, the data distribution, the class distribution, is actually also quite balanced here between the two classes. And finally, for our next two models, lambda rank and lambda mart, they are both pairwise models like RankNet, but they require the data to be provided in a listwise format. That is, for each query, input should be the top k documents along with a numeric score indicating its relevance. So the prompt here provides a query and a document as before, but there is also the description of a scoring rubric, which asks the LLM to, and then it asks the LLM to provide a score. So I initially tried with the 3-point scale, 1 to 3, but results were not very good. So I tried this 5-point scale that you can see here. And if you recall from the results slide I showed earlier, both the models trained on this data perform relatively poorly. And I think it's because the resulting distribution that you can see here of the classes is quite imbalanced, right? And moreover, I think in general, numeric scores may be harder for the model to generate accurately compared to binary judgments, just as it's harder for human experts because of the qualitative nature of the judgments and the scoring, right? So now that we have seen the labels, we will now look at the feature generator. For those of you who have used scikit-learn, the label generation process is, we just discussed, are the Y values, right? The list of labels. And now what we'll do is we'll generate the X values. So essentially, it means that we convert the query document pair into a vector of numeric features such that the ML model can consume. And this is where we might need some domain expertise, at least the way I have done it here. But you don't really need to. I mean, if you're in a new domain where you don't understand the data too well, another option could be to just create a feature vector by encoding the query and document using a suitable embedding model. This strategy is similar to how you would approach fine-tuning a vector-based retriever in a reader-retriever search pipeline. The embedding vector is analogous to a manually created feature vector, except that it's just not as interpretable because it's all 300 dimensions or 500 dimensions or whatever. And depending on how well you know the domain, it may or may not be better than a manually created feature vector. So I went ahead and did it anyway because I thought I could do a better job than just using an embedding. So the approach I took for feature generation is to manually choose features and encode them in a feature vector. It is inspired by the features described in this Microsoft Learning to Rank Datasets website. And at a high level, you can classify features as query features, document features, or query document features, depending on where they came from. In addition to the queries suggested in the Microsoft website, I added the concept overlap that you can see here, the concept and the semantic group overlap. This is from a knowledge graph, and the idea was to bring some knowledge graph awareness into these features. And there is also the cosine similarity feature, which brings some awareness of the semantic similarity between these fields and the query, right? So, and for each of these highlighted features, these are essentially field level features. We compute the value for these 4 different fields here: the title, the section title, the breadcrumbs, and the text. And the effect is that you kind of bring some content awareness into the features, right? So in the sense that these are the fields that are important for our search application. And for each of these per field term frequency or TF and term frequency, inverse document frequency, TF-IDF features, for each field, we capture multiple aspects of this, right? Such as the minimum, the maximum, the mean, and standard deviation. And the idea here, again, is to provide the model with an awareness of the shapes of these features. So I also wanted to cover where we got these features from. So you could use it as a template for your own starter features if you were to implement something like this. Some of these features are generated just by counting, right? Such as the number of query tokens and overlapping query tokens and query concepts, respectively. So these are the ones in blue here. And the TF-IDF document features and the BM25 scores are generated using Elasticsearch's term vector and search services, respectively. So you can actually make these are generated from the Elasticsearch index based on its own statistics. The entity and knowledge graph features are generated using KMiner, our proprietary dictionary-based NER system that recognizes the entities in our medical knowledge graph. And vector similarity uses the pre-trained sentence transformers model to compute the vectors and cache them in a quadrant vector store from which they are retrieved during feature generation. And using these sources, in all, we have 61 features per query document pair. So now let's look at the model. As I mentioned, we have a training pipeline and an inference pipeline, and the model appears in both, obviously. In the training pipeline, the trained LTR model is the output of the pipeline, and in the inference pipeline, the LTR model is used to re-rank incoming search results. And this is the part where I promised to give you some background on LTR. So LTR is a large and active field of research. But LTR models in general can be classified as either pointwise, pairwise, or listwise. The classification identifies the kind of input they consume and the kind of ranking information they learn to provide. So in our diagrams, I show the input as query and a document, while LTR models are not very much different from, say, scikit-learn models, which I think most of us here are more familiar with anyway. So the query and document pair inputs and the triple in case of RankNet, right? In the case of RankNet, you have the triple, are converted into a feature vector by the feature generator we just talked about. So once that happens, input to the model is just a matrix of features, each row corresponding to a single input, and output is a list of labels, one for each input. So feature vectoring, judgment prediction out just like any old scikit-learn model. So I have shown this chart before, at least actually both these charts before, but just to recap, I tried training 4 different LTR models. They're represented by the blue bars in the top histogram here. The red dotted lines represent the 3 baselines we evaluated before building the models. In terms of performance of the various LTR models, you would expect lambda mart to perform the best, followed by lambda rank, then RankNet, and then the regression model. However, in our case, we observed that RankNet performs the best. And as I mentioned earlier, I think the poor performance of the lambda rank and lambda mart may at least have something to do with the unbalanced nature of the data that we gave it, it was trained with. So in terms of implementations, when we talk about LTR models, usually people think of LTR plugins that are available as part of Elasticsearch and Solr or other platforms as well, search platforms. So I thought about going that route initially, but that would mean messing with configuration for a search index that is being currently used by other developers, which seemed risky, so I built this pipeline instead with standalone models. So from an implementation point of view, pointwise regression is the simplest and most intuitive. It takes a vector generated from a query document pair and learns to return a number between 0 and 1, or a binary judgments, relevant or irrelevant. So as far as implementation goes, I built a 2-layer fully connected neural network, but you can get comparable results with a scikit-learn SVM-based classifier or regressor as well. I tried. It does have very, very similar results. So the other 3 are pairwise models. RankNet is the first pairwise model. It takes a query and a pair of documents and returns a binary classification as to which document is more relevant. I implemented it as a 3-layer Siamese network. And for the other 2, the lambda rank and the lambda mart, I adapted the code that was in the L2R repository, which I have linked to here. Both of them need the input in a listwise format called SVM Lite. So I have pre-processing code in there to build, from my scored judgments, I build the SVM Lite format. And this is because they need the ranking and scores for training, both the ranking and the scores, right? So internally, they convert the input to pairwise and use the scores to learn the difference. Oops. Sorry. And internally, they convert it to pairwise. And give me a second. Yeah, sorry. So that helps them learn the score, the relevance labels faster. And this part with the DMLC XGBoost, I found out about later, but turns out that I could have also used XGBoost with the rank objectives that are shown here to get the lambda rank and lambda mart model implementations. But by that time, it was kind of quite late, so I ended up not using it. So there is an additional step for RankNet that I wanted to cover. As you may have noticed in the pointwise lambda rank and lambda mart models, the output is a numeric score, which can be used to rank the documents directly, right? However, the output of RankNet is either -1 or +1, depending on which document is more relevant. So in order to generate a document ranking from this information, we need a rank matrix, which is just a matrix of scores for document pairs. In this example here, we have collected a bunch of relevance judgment predictions for documents D1 to D5, which you can think of as maybe the top 5 results for a query. And we want to produce a ranked response for those top 5 results. So in the matrix, the elements along the diagonal are obviously 0, since all documents are as relevant as themselves. And the upper triangular matrix is a mirror image of the lower triangular matrix, since if document D2 is more relevant than D1, then D1 by necessity has to be less relevant than D2, right? And once we have this matrix, -1 + 1 fill the matrix up, and then we just take the row sums of each, and then we rank using the row sums. We re-rank the documents using their row sums. The approach requires us to do n times n-1 over 2 comparisons before we can generate the rank list. So you would need to generate around, for top 50 results, for example, you would need to generate around 1,200 predictions. So that is one thing to think about. And the blog post link here that I've linked to below, it has more information about this technique. So one other thing to note is that all our pairwise LTR models are related to each other in a kind of an evolutionary way, right? So Chris Burgess has written a paper on this. It's a very informative paper. If you are curious, you should go read this. So basically, all of them learn by gradient descent. For RankNet, the gradient is the difference of cost to swap a pair of documents plus versus the difference in their scores. Now, lambda rank is an improvement over RankNet in that the gradient is multiplied by the difference in the NDCG scores of the pairwise being, the pair being considered, right? And the lambda in its name refers to this product of, gradient and the NDCG difference. And the net result is that it leads to faster convergence, and the results tend to be more in line with search relevance expectations. And lambda mart takes a slightly different approach. It uses gradient boosting, which is a bagging mechanism. So it works by iteratively combining weak learners that focus on addressing the errors observed in the previous weak learner. So if you think in terms of decision trees, as you can see in this diagram here, you might first focus on a tree that uses a small subset of features and check its performance, and then add another tree with another subset that together addresses the errors made by the first one, and so on, right? And so lambda mart is basically a combination of mart, multiple additive regression trees, a type of gradient boosting technique, and it calculates the lambdas similar to how lambda rank does it, hence lambda mart. So in any case, in order to determine now which re-ranker performs the best for our use case, we needed a way to evaluate it, and that's our evaluation bit right here. So to evaluate a query document pair, we provide it to an LLM and prompt it to generate a relevant pair, identical, in fact, to what we did to generate labels for the pointwise model. We then roll up these judgments across all top 10 documents in the results for the query, giving us precision at 10 score for the model for the given query. So let's say for some query, the LLM said 7 results out of the top 10 were relevant. So in that case, our precision at 10 would be 0.7. And if it said 3 results of the top 10 were relevant, then it would be, P at 10 would be 0.3. So we then roll up these scores across all our queries in the gold set, giving us the mean average precision at 10 or map at 10 for the model. So we evaluate all 4 models using the same fixed list of queries. So we have a comparative score so we can rank them. And one thing to note is that even though, so search is generally regarded as a rank-aware application, a rank-aware application, right? However, mean average precision is usually thought of as a rank-agnostic metric because it doesn't have any idea of the ranks here. So the reason we use map instead of other metrics is because our application needed all top 10 results to be treated as equally relevant. But in applications where ranking matters, this pipeline can be trivially adapted to generate rank-aware metrics, such as NDCG at 10 or MRR at 10 as well. So next, let me sum up what we talked about and look at how we can improve further. So to conclude, the LTR approach yields high relevance models quickly and with relatively little effort compared to the traditional approach to building search applications. This is because LLMs address one of the main bottlenecks for LTR adoption, that is the difficulty of creating enough labels of sufficiently high quality to train LTR-based relevance models. And thus, LLMs can be used to jumpstart the development of an LTR-based pipeline in environments or domains where this wasn't an option earlier, right? And because human judgments are difficult and expensive to acquire, using machines to do that seems to make sense. And it seems like a good option to consider when building your own next search application. In addition, unlike purely statistical or purely knowledge graph driven or purely vector-based approaches that people generally go for in search pipelines, the feature generation step in our LTR approach allows developers to inject information from various sources. So you can actually mix and match potentially good ideas from different kinds of pipelines. So in that sense, it's actually, I think, it's superior to just using one method. So the other thing I wanted to point out is that while I built the first two LTR models from scratch and adapted the last two from existing code bases, they're all fairly standard, well-established general purpose models that people have experimented with and have found to be effective. So nothing much to do there to improve things, really, right? But I think the main innovation here is that we use LLMs to generate judgment labels, and there may be scope for improvement here. So during an error analysis exercise, we found that our original assumption that LLMs can accurately mimic human preferences was not completely accurate. And while there was a large overlap, around 70% between human and LLM judgments, in general, LLMs tended to be more lenient than human experts. And you can see it reflected in the charts at the bottom here. So in the leftmost one, we have a confusion matrix. And you can see a lot of cases here where the human has provided an irrelevant judgment, but the LLM thinks it's relevant, right? Similarly, if you go to the rightmost one, the orange, the distribution curve is basically the human, represents human judgments, human scores, and the blue one represents the LLM scores. And as you can see, there is a fair bit of overlap between the two, but the LLM tends to assign higher scores. And the middle one shows the correlation between the two different kinds of scores. And as you can see, the correlation coefficient is around 0.4, which is on the low side. And you can also see that LLMs tend to make more mistakes as the relevance increases. And
I apologize for interrupting. We do have just like a minute and a half left. If you want to start wrapping things up, and then you can continue any conversations over in Discord.
Okay, thanks. So, all right, so anecdotally, based on what we see in their analysis, I found that the LLM tries a bit too hard to predict relevance and makes some leaps of reasoning where the human would not consider valid. So I think that's the main area we would focus on future work. And I'm going to go really quick. One way we thought of is to use an active learning pipeline. And the idea here is that successive iterations will make it better. And each time you take low confidence judgments and you have humans annotate those pieces. The second one was using like a mixture of experts, multiple LLMs to ensemble it. And we saw that this is the diagonal is the majority decision and the correlation with the LLM. And we saw that Claude had pretty good results here, which is why we used it. And the third one is like the prompt engineering thing I was using is fairly basic. So there are things that I plan to do with better prompting, right? And I think that's it. Thank you very much for being such a great audience, and staying with me so far. And thanks to PyData Global organizers for providing me a platform to share my ideas and finance the community. The source code is here. I've also shared on Discord, and I can take questions if there is time, or we can go to Discord and I can.
We're actually out of time, but you can, like you said, join everybody in Discord and continue those conversations. Thank you so much for your time today.
All right, thanks.